Boeing's Starliner spacecraft is gearing up for a critical in-orbit hot fire test of its thruster system at the International Space Station, ISS. The test, set to take place either on Saturday, July 27th, or Sunday, July 28th, is essential as NASA and Boeing work to resolve the ongoing investigation into thruster malfunctions and a helium leak that arose during the current mission, known as the Crew Flight Test, CFT. This trial will focus on the spacecraft's reaction control system, RCS thrusters, 28 in total, though only 27 will be activated, as one has been deemed inoperative for the return journey. Commands for this crucial test will be sent from Mission Control on Earth, but there is a strong possibility that NASA astronauts Butch Wilmore and Suni Williams, both aboard the ISS, may get involved. Their experience as former U.S. Navy test pilots and their keen interest in the mission make them likely participants. Steve Stitch, who manages NASA's Commercial Crew Program, emphasized that the main goal of this test is to confirm that the thruster system functions as expected before the spacecraft undocks. This includes a vital verification of the helium system, which hasn't been thoroughly assessed since June 15th. Engineers will pressurize the manifold and perform a hot fire of the thrusters, all while monitoring helium leak rates to ensure the system's stability. Originally, the CFT mission was supposed to last around 10 days after launching on June 5th. However, the unexpected issues with the thrusters and helium leaks have resulted in an indefinite extension of the mission, giving engineers more time to troubleshoot the problems. Despite these challenges, the spacecraft successfully docked with the ISS. Ground tests conducted earlier in July at the White Sands Test Facility shed light on the technical difficulties encountered during docking. For example, a test thruster from AET Rocketdyne, which had been in storage for 3 years before testing, exhibited severe valve degradation caused by nitrogen dioxide vapor. The propellant flow was hindered by a swollen seal, and the high temperatures led to Teflon erosion. Bubbling was also detected in a downstream filter. Stitch noted that the thruster behavior seen in orbit was consistent with these ground test findings. Although the RCS thruster design, the White Sands Test Facility provided valuable insights into the technical issues encountered during Starliner's docking with the ISS. For example, a thruster from Aerojet Rocketdyne, similar to those on the Starliner spacecraft and stored for 3 years prior to testing, exhibited significant valve system degradation. This degradation was linked to exposure to nitrogen dioxide vapor, which caused the propellant flow to be obstructed by a swollen seal. High temperatures also led to Teflon erosion, with bubbling found in a downstream filter. Steve Stitch highlighted that the thruster behavior observed in orbit was consistent with the problems identified during ground tests. While the Reaction Control System, RCS, thruster design has its roots in previous Aerojet spaceflight programs, modifications made specifically for the Starliner service module may have contributed to these issues. The thrusters are encased within protective dog houses, which serve to insulate them from the frigid conditions of space. However, during the crew flight test CFT, the combination of frequent RCS thruster pulses and firings from the Orbital Maneuvering and Attitude Control System, OMAC, caused the thrusters to heat up more than anticipated. Stitch proposed that the solution to this problem might involve adjusting the way the thrusters are used during flight, rather than making fundamental changes to the design. These discussions are ongoing, with senior-level reviews scheduled for the upcoming week, including contributions from NASA's Aerospace Safety Advisory Panel. Mark Nappy, Boeing's Commercial Crew Program Manager, added that Aerojet Rocketdyne has been working closely with Boeing throughout the mission to find potential solutions. These include replacing the seals or modifying the thermal protection inside the thruster housings. Additionally, future crew missions may follow a revised flight profile to the ISS to mitigate these issues. Despite the unforeseen challenges, the Starliner spacecraft remains certified for emergency scenarios. Boeing and SpaceX, both awarded billions under NASA's Commercial Crew Program contract in 2014, have taken different paths in their development. While SpaceX has successfully launched 11 crews to the ISS since May 2020, 8 for NASA and 3 for Axiom Space, Boeing's Starliner continues to navigate the complex challenges of its development. The upcoming hot fire test is a critical milestone for Boeing and NASA as they work to resolve the ongoing thruster and helium system issues. Each step of this extended mission provides engineers with valuable data that will influence future Starliner flights. With continued collaboration and thorough testing, Boeing is determined to ensure that Starliner becomes a reliable and safe spacecraft for NASA's crewed space missions. As the mission unfolds, the lessons learned from these setbacks are essential to building a stronger, more dependable system for the future. On a related note, if you haven't already subscribed to our channel, now is the perfect time to do so. We regularly share exciting content about SpaceX, space exploration, and more. Don't forget to turn on the notification bell so you never miss an update. Shifting focus to SpaceX, the company faced a significant setback on July 11th when its Falcon 9 rocket encountered a failure during a launch carrying 20 Starlink broadband satellites. The launch initially went smoothly, with the rocket's first stage performing flawlessly. However, trouble arose when the upper stage suffered a liquid oxygen leak, preventing it from completing a critical orbit-raising burn. As a result, the Starlink satellites were deployed at too low an altitude, re-entering Earth's atmosphere prematurely and burning up. After investigating, SpaceX identified the root cause of the failure. In a July 25th update, the company revealed that the issue was traced to a crack in a sense line for a pressure sensor in the vehicle's oxygen system. The crack was caused by fatigue due to the high loads generated by engine vibrations, compounded by a loosened clamp that typically secures the line. Despite the initial successful burn by the upper stage's Merlin engine, the subsequent leak prevented it from completing a crucial second burn needed to circularize the orbit, which was essential for proper satellite deployment. The leak had a significant impact, leading to excessive cooling of critical engine components. This cooling was especially detrimental to parts responsible for delivering ignition fluid to the engine. The unexpected cooling triggered a hard start rather than a controlled ignition, which damaged the engine hardware and ultimately caused the upper stage to lose its attitude control. Although the upper stage did manage to deploy all 20 Starlink satellites, the compromised orbit meant that the satellites re-entered Earth's atmosphere much sooner than intended, burning up during re-entry. The anomaly investigation, led by the U.S. Federal Aviation Administration, FAA, concluded that the root cause of the failure was the crack in the sense line. This crack was aggravated by vibrations from the engine and the looseness of the clamp that normally secures the line. In response, SpaceX has swiftly implemented measures to prevent a recurrence of this issue. For upcoming launches, SpaceX will eliminate the failed sense line and sensor from the second stage engine. These specific sensors are not essential to the flight safety system and can be effectively replaced by other existing sensors on the engine. The new design has undergone extensive testing at SpaceX's rocket development facility in McGregor, Texas, with enhanced oversight and qualification analysis conducted by both the FAA and SpaceX's internal investigation team. In addition to these design modifications, SpaceX has carried out a comprehensive qualification review and inspection of all sense lines and clamps across their active booster fleet. This proactive approach led to the replacement of components in certain areas to avoid similar issues in future missions. The July 11th incident marked SpaceX's first in-flight failure since June 2015, when a Falcon 9 rocket disintegrated during the launch of a robotic Dragon cargo capsule to the ISS. Another notable setback occurred in September 2016 when a Falcon 9 exploded on the launch pad during pre-flight testing, resulting in the destruction of the Amos 6 communications satellite.